The universe, from the graceful pirouette of galaxies to the frantic jitter of subatomic particles, is a stage for motion and interaction. Within this grand cosmic theatre, the 11-dimensional model proposes a unifying framework where seemingly disparate phenomena are interwoven through a complex tapestry of interconnected dimensions. Central to this model are the principles of rotation and polarity, which we have explored as fundamental organizing forces across all scales. Building upon the intriguing anomaly of the Dzhanibekov effect, the counterintuitive flipping of a rotating body with unequal moments of inertia, and the macroscopic synchronization observed in collective systems, we can envision a novel experiment designed to probe the very nature of entanglement and potentially illuminate one of cosmology's most enduring mysteries. Dark matter. This essay will outline this proposed experiment, detailing its variables and predicted outcomes, and speculate on how its results, interpreted through the lens of the 11-dimensional model, might offer unprecedented insights into the interconnectedness of the cosmos and the elusive nature of dark matter. The Dzhanibekov effect, a captivating demonstration of classical mechanics in action, reveals the complex rotational dynamics of objects with asymmetric mass distribution. The periodic and seemingly spontaneous 180-degree flip of an object, spinning around its intermediate axis in a zero-gravity environment, highlights the inherent instability that can arise from the interplay of a body's inertial properties and its rotational state. This macroscopic rotational polarity shift, driven by internal dynamics rather than external torques, provides a tangible entry point for exploring analogous phenomena at the quantum level and within the broader context of the 11-dimensional model. Extending this intriguing effect to a multi-body system in zero gravity, we arrive at the core of our proposed experiment, a collection of several identical objects, each carefully prepared to undergo the Dzhanibekov flip. The initial phase of the experiment would involve inducing a synchronized flipping motion in all the objects, perhaps through a simultaneous application of a brief external torque, or by initiating their rotation with precisely matched parameters. The key question then becomes, what happens to this synchronized choreography as the spatial separation between the objects is systematically increased? To thoroughly investigate the potential for macroscopic entanglement and its connection to the 11-dimensional model, this experiment would need to control and vary several key parameters. Initial synchronization method variable, the method used to initiate the synchronized flipping. Predicted outcomes, simultaneous start. If all objects are set spinning around their intermediate axis at precisely the same time with identical initial conditions, a degree of initial synchronization is expected. External pulse. A brief, non-contact external pulse, such as a weak, uniform magnetic field if the objects are slightly magnetic, or a carefully timed burst of air applied simultaneously to all objects could induce a more tightly synchronized initial state. Gradual entrainment. Observing if synchronization emerges spontaneously over time from slightly different initial conditions, mimicking the human bridge example. Spatial separation variable. The distance between the centers of mass of the rotating objects, ranging from very close proximity to significant separations within the confines of the zero-gravity experimental chamber. Predicted outcomes, close proximity, stronger and more stable synchronization is expected due to potential subtle interactions through shared fields or even minute gravitational influences, increasing separation. If the synchronization is mediated by local fields alone, the effect should weaken and eventually disappear beyond a certain threshold distance. However, if the 11th dimension facilitates a non-local exchange of rotational polarity information, the synchronization might persist even at larger separations, albeit potentially with a time delay or a decrease in the strength of the correlation. Number of objects. The number of objects undergoing the Dzhanibekov flip can vary, ranging from pairs to larger groups. When we look at pairs, we observe the synchronization and its breakdown in the simplest multi-body system. But when we move to larger groups, it gets interesting. We investigate the emergence of more complex synchronization patterns, the stability of the collective behavior, and how the loss of synchronization in one object affects the rest of the group. This could help us explore the information processing capacity and the resilience of what we call macroscopic entanglement. Inertial properties, also known as moments of inertia. Here, we use objects with precisely measured but varying unequal principal moments of inertia. If the objects have identical inertia, the most robust and stable synchronization is expected. However, if there are slight variations, small differences in inertial properties might lead to phase lags in the flipping motion or a less perfect synchronization. This could potentially reveal the sensitivity of the entangled state to individual object characteristics. On the other hand, significant variations could disrupt synchronization altogether, suggesting that a degree of similarity in fundamental properties is necessary for the emergence of collective behavior. Rotational frequencies. We initiate the rotation of the objects at different but controlled angular velocities around their intermediate axes. If the frequencies are matched, synchronization is expected to be more readily achieved and maintained. With slightly different frequencies, the synchronization might take longer to establish, or the system might settle into a more complex state of near synchronization with periodic phase shifts. This would reveal the sensitivity of the collective behavior to individual object dynamics. But if the frequencies are significantly different, synchronization might not occur at all. This indicates a limit to the range of frequency mismatch that the interconnectedness can overcome. Introducing subtle uniform fields, whether gravitational or electromagnetic, if the objects are designed to interact with them minimally. Let's talk about the predicted outcomes. First, no effect if the synchronization is primarily mediated by the 11th dimension or very weak local fields. A weak uniform external field might have no discernible impact. Second, enhanced synchronization. Certain field orientations or frequencies might resonate with the object's inertial and polar properties, potentially enhancing the synchronization effect by providing a common external influence. And third, disrupted synchronization. Other field configurations might introduce competing torques or energy gradients, leading to a breakdown of the synchronized motion. Intentionally altering the rotation, whether it's the speed, axis or polarity of one synchronized object. Now let's consider the predicted outcomes. First, damped resynchronization. The perturbed object might gradually return to the synchronized state with the rest of the group as energy and angular momentum are redistributed through their subtle interactions, potentially mediated by the 11th dimension. The timescale of this resynchronization would provide information about the strength of the interconnectedness. Second, cascade effect. The perturbation of one object might trigger a cascade of adjustments throughout the group, leading to a new synchronized state or even a complete desynchronization, depending on the strength of the perturbation and the interconnectedness of the system. The 11-dimensional model posits the 11th dimension as a realm of ultimate interconnectedness, potentially operating beyond the constraints of our familiar four-dimensional space-time. The hypothetical synchronization observed in this experiment, particularly if it persists across significant spatial separations or emerges spontaneously, could be a macroscopic manifestation of the principles governing entanglement at the quantum level. The 11th dimension might provide the higher dimensional pathways or the fundamental fabric that allows for a subtle, non-local exchange of information regarding the rotational states of the objects, leading to their coordinated behavior. The strength and speed of this synchronization, as explored through the experimental variables, could offer clues about the properties and dynamics of this higher dimensional interconnectedness. The mystery of dark matter, the invisible substance that exerts gravitational influence but does not interact with light, remains one of the most profound challenges in modern cosmology. The 11-dimensional model, with its expanded view of reality, offers speculative avenues for understanding this elusive component of the universe. If the 11th dimension facilitates interconnectedness and potentially allows for phenomena that are non-local in our three-dimensional space, could dark matter be matter or energy that primarily resides or interacts within these higher dimensions? Its gravitational effects could leak into our three-dimensional space, explaining the observed gravitational anomalies in galaxies and galaxy clusters, while its limited interaction with electromagnetic forces, light, would account for its darkness. The proposed experiment, despite operating at a classical macroscopic scale, offers a tangible and potentially intuitive model for grappling with the counterintuitive nature of quantum entanglement. The synchronized flipping of the Dzhanibekov objects, correlated across space without any obvious direct link, mirrors the spooky action at a distance that characterizes entangled particles. By manipulating the experimental variables, we might gain insights into the factors that strengthen or weaken these correlations, providing macroscopic clues about the fragility of quantum entanglement and its dependence on the isolation of quantum systems from external information. The breakdown of synchronization upon the introduction of a measurement altering the state of one object could be particularly relevant to understanding the collapse of the wave function in quantum mechanics. The proposed experiment involving synchronized objects undergoing the Dzhanibekov effect in zero gravity represents a novel and potentially transformative approach to probing the fundamental nature of interconnectedness, entanglement, and the enigmatic phenomenon of dark matter. By systematically varying experimental parameters, such as spatial separation, number of objects, inertial properties, and external fields, we can explore the dynamics of this macroscopic entanglement and its sensitivity to external influences. The 11-dimensional model provides a compelling theoretical framework for interpreting the results of such an experiment, suggesting that the observed synchronization and its breakdown might be macroscopic echoes of the higher dimensional interconnectedness that governs the quantum realm. Furthermore, the model opens speculative avenues for understanding dark matter as a manifestation of matter or energy residing or interacting primarily within these higher dimensions, its gravitational influence subtly permeating our three-dimensional space. While requiring significant technological and logistical hurdles, This cosmic chorus experiment holds the tantalizing promise of bridging the gap between the classical and quantum worlds, offering unprecedented insights into the fundamental architecture of the Everyverse. Thank you for watching. If you enjoyed the content, please like, subscribe and share.